तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lectures on design aspect, we concentrated on design of simple circuits, both combinational and sequential, more in the nature of a review. Of course, we introduced a few new concepts like multiplexer based design and how to fit in a design into a given PLD and all that, but basically it is simple circuits which are familiar to you, and most of you might have seen these circuits in your earlier course on digital systems. So, we have to move on, and in a real digital system design you need to think of system concepts. Given a problem, how do you approach the problem, how do you approach the design, what steps would you make to make the design possible. And of course, when you reduce that problem to a set of blocks and a set of specifications, then of course we will go back and use the known techniques of both combinational sequential design. So, today we are going to start a new sort of a topic where we will look at the circuit, the system as a digital, the design as a system aspect. We will take an approach of what is known as a top down design. That means you are given the specifications, you understand the specifications, partition the specifications into realizable blocks and try to implement those blocks using the technology as well as tools available at your disposal. This is different from the circuit based approach where we wanted an adder and we know how to do it based on the either the gate level corner map simplification or using a available component. So, in the top level design, what is generally done is to partition the given problem into two parts. You have what is known as a architecture of the design of the system you are designing. Some people call it data processor. This name came because most of the digital design was originally meant for computers. So, we call it data processor, but we can also call it architecture. What it does is really this is the functional block actually, the function that you want to implement finally as a multiplication or some computation, whatever is the function you are looking at will be realized by this processor or the architecture block. But how does it know what it should do, and more importantly how does it know what sequence it should do. So, it needs control signals. So, the data processor will have inputs and outputs which are data in and data out. So, in the case of a multiplier, it could be x and y, the data in, and product of x and y could be data out. But as I said, how do you know when you start the multiplication? How do you know in what sequence you go over and multiply row by row? All that has to be provided to this functional block. So, we have another block called a controller. The job of the controller is to give signals to the data processor so that it can be done effectively. These signals are called command signals or simply commands. Based on a command, the data processor initiates any action. And how does the controller know when to give command? It cannot keep on issuing commands regardless of what happens in the data processor. So, of course, it needs some information back from the data processor. So, that means we also need some signals back from data processor into the controller. These signals are called status signals. So, basically the data processor is the functional block. Data processor, as I said, do not attach too much importance to this phrase, because as I said, these things come because of the computer jargon. Any functional block, it could be a traffic light controller where it will be a light which turns from red to green or green to yellow to red, whatever. That is also a data processor. That is why I said architecture in general. It will have its own input and output, need not have input and output sometimes, but more importantly it should have commands received from the controller and status given back to the controller. Likewise, the controller also may have to receive some signals addition to the status signal. When do you know, when do you start the multiplication? The command controller gives the signal for step by step execution. It tells you when to load a particular register, when to load the second register, when to put the result back. So, these detailed sequences may come from the controller, but the overall start of the whole process may depend on some external activity. When do you want to carry out the multiplication in the entire algorithm? If you consider the algorithm in totality, when do you want to do the multiplication? This will also have to come from the controller, this has to come to the controller. These are also inputs, but these inputs are called external inputs. So, controller has two sets of inputs, one from external sources, the other from the internal process. Likewise, the controller may also have, in addition to giving commands, may also give you the status of what is happening. The multiplication is done, result is ready, that signal has to be displayed so that you go on take the next step. So, we also need external outputs. This is how you can partition a system, a digital system to be designed, and once you partition it, it becomes easier to implement, because data processors are usually elements which are available, functional blocks which are available. A multiplier can be bought, registers are available off the shelf, it can be an adder which can be purchased. So, most of the time the architecture functional blocks with the architecture are available off the shelf. Sometimes you may not have the exact specification, but you may have to work with that. On the other hand, the controller is what you design, this is specific to the problem you are designing, specific to the design. It is designed by the designer. So, the designer's job is to, given a problem, understand which part of it can be implemented as a functional block which is available readily, and what extra things he needs to put in order to use those functional blocks in a proper way to achieve the desired goals. So, this partitioning of the problem, understand the specifications of the problem, completely, it should be foolproof, there should be no vagueness about it. If there is a vagueness, then it is very difficult. Then you partition. After understanding the specifications, you partition. The partitioning will be done taking into account what is available and what is not available. So, it takes into account available functional blocks. And once you have these available functional blocks, then you also know what are the input output specifications of this functional block, each of these functional blocks. In addition to the data processing ability, take an example for a register, example of a register. You want to use a register as a functional block, one of the functional blocks of the architecture. A register is meant to store data. So, there should be data in, and if you want to read the data from the register, data out. So, this corresponds to data in, data out. There is no problem. But what we should also know is, does the register have a load feature? Does the register have a clear feature? These are the extra things, the control signals available. So, for each functional blocks, which can be used by the controller as status signals. So, after having partitioned the problem to choose the proper partition takes into account functional blocks, which means basically choose the functional blocks. After having done this, I should now find out the control signals or not find out, it is there, list, let us say, list the control signals available to be used in the controller, in the controller design. It can be an input signal or an output signal. Control can be an output control. That means I can get a control signal going back to the controller, or I can have a control signal which can come from the controller into the unit. Both of them are to be identified. With this, I have an idea of the controller itself. So, that means I need to get a block diagram of a controller. As I said, external inputs, external outputs. These are the control signals which are available coming from functional blocks. And these are the signals going to the functional blocks. Each one of them I should be able to map. Each of these signals I should be able to map to one of the signals available in the functional block. Each one of this I should again be able to map to the functional blocks. That means I should be able to define very clearly which signal of the functional block is connected to which signal of the controller, either as an input or an output. That is a clear definition. We have to do that. That way, once we design the controller, we can directly connect it together and it will work. Now, having done this, I take into account the operational requirement. We have only designed the functional blocks. We have not talked about how to carry out the design, how to carry out the operation required to be performed by the functional unit. So, this will be represented by this will be explained, or this will be described by means of a procedure. So, I need to draw a procedure of control. Procedure for the controller operation. Actually, we do not use the word procedure, I just first wrote it so that you will understand what it is, but really this is what is known as algorithm. Procedure is nothing but an algorithm. So, actually I will replace this word by algorithm. That is the difference between algorithm and the program. Program is an algorithm. Once you write an algorithm in software for a specific computer, it becomes program. Whereas algorithm is the series of steps required in order to execute a particular operation, particular sequence of operations in order to achieve the desired goal. So, this algorithm of the controller will now take into account the input specifications, output specifications, available signals, their status, and when do you give the required commands to the external functional units. All this will be taken, and this is done by means of what is known as a chart called ASM chart. ASM stands for algorithmic state machine. That means it is a step by step, a clock by clock sequence of operations. The algorithm or the procedure of the controller is defined clock by clock in order to complete the given problem, given design, given specifications. This is similar to flow chart in a sense. Flow chart also does the same thing for a computer program. In a computer program, before you write a program, you write a flow chart. But the difference here, we are now accounting for clock by clock operation. That is why it is called a state machine. So, term algorithm is common for computer program as well as this hardware design. Algorithm is generally used by computer people also, but there we do not talk about, we only talk about functions or tasks. We say get numbers from memory, multiply, put the result back, even that is detailed. People will say multiply x and y. So, that will be one block completely. In a block, in a flow chart, one block could be simply multiply a and b or multiply x and y. Here I cannot afford to say that. Here I have to say get x, get y, multiply. Now, the problem is even there, even here, even this is not adequate. I have to say, I have to take into account how many clock cycles does it take for me to get the data from x, how many clock cycles is going to take for me to get data from y, and how many clock cycles is going to take for multiplication, and what do I do till the multiplication is over? Should I wait? Should I go and do something else? All of these things are very detailed descriptions are required. So, this is a hardware flow chart. Accounting for each clock cycle and each signal, both input and output. In other words, once you have this algorithmic state machine chart drawn, the hardware is realized very quickly, very simply. So, once you have an algorithmic state chart, the design of the controller is only a mapping process, which is a general technique. You do not need any more intelligence. So, from ASM The next step is I will say design the hardware, design controller, or I will not even say design, I will say implement controller using ASM. This implement also is a too big a word, I will rather say map it. There is something which is there, is something like this standard set procedure, it is a rule based design. So, as I said, it is a rule based design, or I will not see even rule based design, it is a mapping process, that is the most appropriate word for it. It is a mapping process. Hardware availability, I mean hardware availability not the functional level, like you want to do with gates or multiplexers, ROM, programmable logic array, that decision you make, and on that hardware chosen you map the ASM. One question is, how is it different from a state machine, because we just talked about in the last lectures about sequential circuits and design of sequential circuit using state diagrams. A state diagram and ASM chart are identical in one sense. There is no new information that we will get in an algorithmic state machine chart or ASM chart that is not found in a state graph. ASM chart is another way of writing the state graph. Here you have a feel for the hardware here. As you go in the state graph, even though it is a hardware design is possible, once you have a state graph you have a standard technique by which you can design the hardware in terms of gates or multiplexers or ROM, PLA, all is understood, PAL. But here when you draw the ASM, you can sort of feel the hardware, you can, it is sort of cycle by cycle operation. There also it is cycle by cycle, let us say you stay in a state and verify the signal, if the signal input, if the input is not coming you wait in the same state, otherwise you go out of the state, all that will blend here also. But then here the way it is drawn, it is more hardware friendly, it is more easy or easier to implement it in hardware, and that mapping, as I said, is more evident here. There also it is mapping only, the process of state graph conversion into hardware is mapping, but it is a design process we call it, whereas here the mapping is so evident as you draw the ASM. It looks like hardware friendly, it looks like we are already designing the machine. So that is how the ASM chart is preferred by a lot of designers, it is more and more popular. So what we will do is, in this lecture and a few more lectures, following lectures, we will take some examples. Again I will go over this. We have given a problem in a global level or top level, that is why it is called top down design. In a top level the problem is given, you try to understand what is required to be done, whether there are any functional blocks which can do that job. If the functional blocks are available off the shelf, do not try to design it, get them. It can be in hardware form, it can be in the Verilog, because functional block, when I say functional block is off the shelf, does not mean that you have to go and get it from a shelf. That is it is a way of saying off the shelf means it is available. In this day of Verilog design and IC design, these are blocks which are available, codes of blocks of codes available which can be borrowed and inserted. This is called IP. IP stands for intellectual property. If you develop a core for a particular function like a multiplier, you can use that again and again whenever that function of multiplication is required. So this is IP based design, they call it core based design. In a older concept we used to call it off the shelf components, that is the same thing. The concept is same whether it is an IC design or a discrete design. So you identify the processor functional blocks, clearly find out whether it is capable of delivering the goods in terms of data processing that is required, that is the ultimate goal of course, but identify the command signals required to initiate or activate each of those functional blocks, and identify the status signals that each of these functional blocks will give at different stages. take those into account along with the external inputs and outputs to design your controller. When you go to the controller, identifying the input and output, you can write an algorithm or a procedure for carrying out the control process by a chart known as ASM chart, which is very similar to flow chart, but more detailed and more cycle dependent, cycle specific, more hardware specific, and with that you implement it using one of the standard techniques available for mapping. And as I said, state graph method and these are not different at all. This is only a different way of doing it, which is more convenient and elegant. I will say elegant, convenient and hardware friendly way of doing the same job. So with this introduction, I want to give you, before we go, I am going to talk about a few examples. Before even going to the first example, I am going to give you some rules about drawing state graph, the ASM chart. We know how to draw state graphs. The same rule can apply to ASM chart, but then there are some specific rules, conventions adopted in drawing ASM chart. So it is better to follow those conventions, especially when you are doing a design which is going to be used by somebody else, either for troubleshooting or for later use or later modifications. It is better that you conform to certain standards and norms. So let us first have a quick look at how to draw the ASM chart for a given controller. So first we will spend some time on drawing an ASM chart, then we will take a few examples. Now ASM chart is the simplest chart you can think of. It's not at all complicated. There are only three blocks in an ASM chart. The first box is a rectangle called a state box. It is called a state box. The state box has an input arrow and an output arrow. This represents the state that as we understand, because in a state graph you know that at each clock cycle the circuit or the system resides in a particular state, and the next clock cycle the circuit or the system can change to another state or continue to remain the same state. But you define the state as, in a state graph or in a digital system, a state as the period for which the circuit will not change, nothing will change in the circuit in terms of its behavior, in terms of the input output. In terms of the output, of course input you can always change, but then you have to better to synchronize it. So let us also say input output. So nothing changes during this period between two states. The period between clock cycles, one clock period is a state period also. It is possible the second clock period, the next clock period also the circuit may be in the same state, but still it is called a next state. The next state can be same as the present state, but still it is the next state because it happens in the next clock cycle. So that is the same concept here, the state graph, the state box. So the state box has a name usually associated with it. The name is given here on the left hand top corner outside the box, and inside the box you write the signals that will be generated as output in this state. So we will say list. So in this case let us say load, I will say as an example. Load may be a signal I give to a command signal, I may give to a register to load the input into the register. That signal will be emanated, issued in this state period, and so we will call this state loading state. It does not have to be same, it can be S0, S1, S2, or it can be ABC, it can be anything else, but usually you write something which can be easily understood here. What is happening in the state will be usually understood by looking at the name of the state. And the right hand top corner, again outside the state, you give the binary assignment, state assignment. So each state in a state graph you need, depending on the number of states, you have a number of variables, and those variables have each will have a 0 or 1. So we have a binary a number representing each state, and that number is given here. So, in this scale, for example, I will call this 0 1 1, no specific reason, I am just arbitrary. So, 0 1 1 is a 0 1 1 is a binary value of the state of the variables, binary values of the state variables of this particular system. Then we have a second box known as the decision box. So, diamond with one input arrow and two output arrows. This is where you test a condition. Suppose you want to start, is the start signal available? If it is available, you will want to start and proceed. If it is not available, you will want to wait. So, this could be an example of a conditional verification, or it could be a memory read operation with wait state. We are looking for some data ready signal coming from the memory. So, you can say data ready, if it is no, wait, yes, proceed, like that. So, again usually they put 0 1, 0 1 is generally done, but in real pure ASM design they call it true or false. If the condition is true, what you do, if the condition is false, what you do. Sometimes the condition to be tested is big to be written in a diamond shaped box, they also draw it like this. If there is a lot of things to write, may not be written, cannot be write too much in a rhombus or a diamond based box. So, this, as I said, is a condition box, decision box. And the third box, the third and the last box is called conditional output box. As an example, it could be shift or add, let us say add. In an algorithm like a multiplication algorithm, shift and add algorithm, you know that we do addition and shifting if the multiplier bit is a 1, if you only do shifting without adding if the multiplier bit is 0. It is an example of a multiplier. When you do a multiplication of two numbers, there is a multiplicand, the multiplier. For each multiplier bit, we add the multiplicand and shift it if multiplier bit is 1. Without adding the multiplier, we shift if the multiplier bit is a 0. So, that is a condition based on the multiplier bit being 1, we want to add, otherwise 0. So, you can put a condition whether the multiplier bit is 1, and before it going to the next shift box, you can say add. So, this is an output box similar to this. We generate an output, here the output generated was load, here the output generated is add, but this is done only under certain circumstances of a condition being met. Whereas here once you put a box and within that box when you write the signal, whenever the circuit or the system stays in that state, that signal will be generated during that clock period. During the clock period for which the circuit is in the state, signal load will be generated. It is unconditional output. Here the output will be generated only when the particular condition is met. So, that is why it is called conditional output. This is useful. Otherwise, what we have to do is to put an extra state. Now, after this it can go to this, generate this add signal and go to the next state. If you do not have the conditional output, I may have to put one state for add and then next state one more state for shift, which means I will put one extra state. If you keep adding the number of states, the hardware becomes, the mapping hardware becomes more and more complex. So, avoid that we have this. So, similar to this Moore-Mealy concept, if you remember, in a state machine, with a Moore machine, we have this type of states generate the output. Outputs are associated with states in a Moore machine. In a Mealy machine, outputs are generated with input conditions from a state. In Mealy, the output is defined by what is the present state, what is the present state the circuit is in, and what is the input at that state. The present state and the input decide the output in the case of Mealy, whereas the present state determines the output in the case of Moore. So, this is a Moore output, this is a Mealy output, that is all. If you are familiar with this. So, these are three simple boxes, that is all you can. So, you can draw any algorithmic state machine by what is the state in which the circuit is, what is the signal that is to be tested at that time and conditions that will be tested in that state, what will happen if the condition is true, what will happen if the condition is false, and if the condition is true or false it goes to the respective next state. In so doing it may produce an extra output called conditional output, or sometimes it may not produce an extra output called conditional output. So, this is all there is to it in any algorithmic state machine. So, it is not a complicated affair, but as I said, if you draw it properly it becomes elegant and easily mappable on a hardware. That is why a lot of people use this approach. So, with this introduction we will take a few examples of a state machine design. Let me first take an example of a very simple ASM. Actually, according to our rules of the design, first the problem has to be defined. We have to partition it between hardware and between controller and the data processor or functional units. Identify the signals required to activate these functional blocks, and identify the signals which are given as status from the controller from the functional blocks. Then based on these signals and the external signals you design the controller, its algorithmic state machine, and then implement it in hardware. So, we will have to take that approach. So, let us now design a simple what is known as a bus orbiter. The circuit is simple, but I want to always start with a simple example. So, as a bus orbiter, what is a bus orbiter? There is a bus like a microprocessor system bus or any other bus in any system, and there are several units requiring the use of it, demanding the use. So, it has to be, the bus has to be granted only to, can be granted only to one of the users, one of the requests at a given time. In order to make it simple, we will say there are two signals called grant A and grant B, GA and GB, stand for request from A, system A, and request from system B. Two requests are coming, and the bus orbiter has to give it to, actually you call it RA and RB, request A and sorry, G may be granting, RA and RB. Request from system A and request from system B come, and if bus is granted to system A signal GA is generated, if the bus is granted to signal B, system B, signal GB is generated. This is the overall system, I have not partitioned it yet. Sometimes the partition is so trivial we do not have to, there is no functional unit here, even though the functional unit will come later. The bus, how this GA is taken and released, all that will be functional units. We are not talking about that. We are only talking about the bus orbiter as a design. The whole concept of the design, whole specification design is for the bus orbiter. Since only bus orbiter I want to design, I will not talk about partitioning the system. This happens sometimes. The system is simple. This partitioning is not a very rigid partitioning. This is one thing I forgot to mention at that time. This partitioning is sort of a flexible partition. Some functions are very grey, whether you call it a functional unit or whether you call it a controller part, it is difficult to say. For example, I will give an example. Supposing I want to do a shift and multiply, multiply by shift and add. Supposing it is an 8-bit number I am doing. So there has to be 8 shifts and 8 adds, of course 8 shift and add things. Add may be there or not depending on bits, shift will always be there will be 8 shifts. So I have 2 ways of doing it. I can keep count of in the controller, I can keep count of the shifts. Every time the status signal says 1 shift, I can take the signal as a signal in the controller, update the controller and issue the next signal. So I keep the counter inside the controller. On the other hand, I can put the counter inside the data processor and say when 8 is reached, only then I will give the status complete, otherwise it will keep on going shifting and adding. So this is one example of how I can flexibly use the data processor or the controller for this job. So when the partitions become so vague, of course it is a multiplier which requires adder, for example, shift and add algorithm. It is clearly a function unit. Adder is clearly a function unit. I will not try to implement it using a controller. But there are certain things like keeping count and all that which can be put in either this or that. So that way this is flexible and depending on the circumstances. So I would not like to do 16 times something. Rather than that, I will put in here as soon as the data it keeps going, it becomes when you put the 16 times here, my state graph is going to become extremely big. 8-bit controller, 8-bit multiplier, 16-bit multiplier. For each multiply I put a state, multiply, add, shift, each is a state. I do a big state graph, the controller or the ASM chart will be so big with so many states. Instead I can put a counter here, activate the counter, update the counter, increment the counter by 1. Every time I do a shift, increment the counter by 1. When the counter reaches particular value, I compare the value and then give it. So the number of states required for the controller bit is. So I'm sort of putting some of the controller function into the data processor by putting an extra counter there. Otherwise, my ASM chart is going to be extremely big. So when that is the approach take, and here it is also very difficult to partition it between bus controller and bus orbiter and anything else. Here it is only a simple circuit. So I am not going to try to define or partition this circuit because the first example is simple example I want to give. I am not going to attempt to partition this into hardware or architecture, functional unit and the controller. I will straight away draw the ASM chart. So there are only 2 signals as inputs RE and RB and 2 signals output GF GB. Only thing I need to know is is there any priority. If RA only comes, bus generally goes to naturally goes to GA. If RB comes, the bus goes to B. What if RA and RB come together? Is there any priority you want to have? So we will define a priority. We will say if RA and RB both come, we will say RA has higher priority than RB. We will solve. This is an arbitrarily I am assuming. I have no preference for RA, just like that as an assumption. So with this I will draw the ASM very simply. I have this unit in which the circuit is waiting. I will call this idle state or wait state, idle state. Nothing happens. Like one of these days you sit and wait for a phone call. Nothing happens, right? And the phone call also does not come finally. That is the most disappointing aspect of it. And then you have this signal RA coming. If RA is yes, true, it has to process and give GA. If RA is false, we will see if RB is present. If RB is also false, go back to idle state or sleep some more. Idle. So, if RA is true, GA is given, and I will explain to you, and I will put one more RA verification here. It requires a little explanation, I am going to do it later. And then once RA is taken care of, I see if RB is also waiting. Because RA is priority, we came here. It is possible both RA and RB are present. It is possible that both RA and RB are present, and since RA has been taken care of, we have not bothered to look at RB, now we have to look at RB. So, look at RB. If it is true, what do? I go, and if this is true or if this is true, I go back to, I go and generate GB. If it is false, RA has been taken care of, RB is not there, so I go and wait. On the other hand, here after GB, by the time I finish GB, again RB will be checked one more time, I will tell you why. Same reason. So, this also will be tested one more time, it is true, it continues to be in GB. 0 or false, again a test is RA is waiting. If it is not waiting, I go back. If it is waiting, I go back to this. So, this ASM is very simple. There is an idle state, there is no output. Inside, I remember that I have not put any output in the box, no output, and you keep checking RA and RB in the same clock cycle. And if RA is true, the next clock cycle you issue GB, DA, and keep issuing GA as long as RA is kept high. That is the point here. That is why I put one more RA here. Because I do not want to just issue for one clock cycle when RA is not removed the requests. So, I am assuming that means my RA will be given and it will kept on as long as I want it. The signal RA will be held high as long as I want the bus. Once I have done with bus, then I will have to remove the signal. Similarly, whenever I want RB, GB, I issue a signal and keep issuing it till GB has done its job. So, once GB is given, it will be RB will be held, if RB is removed only then GB will be removed, that is the idea. So, GA will be kept on. If it is after it has become 0 or false, this is usually put arrows here everywhere. RB will be tested one more time, I already told you, because RB has not been considered earlier, and if the RB is true, G will be issued, and again for the same reason RB will be tested as long as RB is 1, as long as RB is true, G will be continued to be issued, and once it is removed, RB is required no more GB is required, RB will be removed, withdrawn. The user will withdraw the request of RB, and then it will go and test RA one more time. It is strictly not necessary because we already tested RA and here, but then by the time it could have, because it would have taken several clock cycles, GB would have been high, by the time RA would have been generated. The idea is again, the priority does not mean when RB has started, RA cannot have a priority. This also is taken care of here. If RA is there before RB starts, RA gets priority, but RB comes after RA start, comes after RB starts, it has to wait till RB is over. That is what it means here, and then takes it back to the original signal, original state, and here also if RB is not there, you go back and wait in the original state. This is the ASM. We will have to map it into hardware, which we will do in my next lecture. This is how you define the system, input signals, output signals, the conditions, specifications will be very, very properly written, like RA comes first, RB comes first, and what will happen if RB comes in between RA, all those will be very clearly defined. Problem specification is about 40% of the problem, ASM drawing is another 50% problem, the rest is 10% or maybe 20%. 40% marks for problem specification, 40% mark for drawing ASM, 20% mark for mapping, for identifying the functional blocks, identifying the input signal, output signal, all that get only 20% weightage. So this is important and this is important, that is why I finished it today. The next lecture what I will do is, I will see how to implement this in the hardware. There are different techniques by which you can do it, we will see those techniques in the next lecture.